done question 1 in the theory portion. You can check it out there. Now, yes, I am eating something. Yeah. So suppose that x to y is continuous. There's a function f from x to y that is continuous. Yeah. So limit points do not need to be conserved. So closures are can be conserved if that makes any sense. Yeah. But the limit points can become a point of A essentially. Okay, I have no idea what the exact thing that's going to happen is, like how to write, you know, the exact behavior. But essentially, take the constant map. That's a very good counterexample. The constant map is not a limit point because you know it is not intersecting a single point other than itself. So yeah, there's only one point to consider, and the inverse image is can have a limit point, but it's not going to turn into a limit. And if you take a Hausdorff space, you're definitely clear because it's T1, and in T1 you have to have an infinite amount of points if it's a limit point. So yeah, and by that I meant R. So yes. So the constant map is a very good counterexample. So no. Okay, question 3. So yes, how do we show there is a direct correspondence between continuity and fineness? So yeah, if we have the same set but different topologies, we are using x and x prime. So let f be a continuous function from x to x prime. Is that it? Sorry. Yeah, x prime to x. And it's I. And I is the identity map, I believe. Yeah, it's important that the identity map. Okay. So yeah, let U be an open set in X. That means what? That means the I inverse of U is so the identity map is a bijective map for the same set. So this is equal to U. And by definition of continuity, it's an open set in X prime. So that means which implies U belongs to tau prime. So open set. So that's actually the definition of continuity. And what does that mean? That means U belongs to tau implies U belongs to tau prime. And that means, well, yep, tau prime is finer than tau. And of course, if I inverse is the inverse map, so is the map from X to X prime. Note that it's a bijection because it's the same set again. So the identity map on the same set is a bijection. So yeah, if I is a homeomorphism, you just apply the same thing in reverse. And so this one and the other one, and then you get they're both finer than each other, and therefore they're both equal. So yeah. Okay, given x naught in x and y naught in y, show that the maps are embeddings. Yeah, so it's essentially the link between x cross y naught and okay, I'll show you. Yeah, so you just need to find the right subset for both of them, right? Since the subset on the other side is x cross y, right? Yeah. Hmm. Yeah. So you just need to find the right subset. So for f, the subset is x cross y naught. So note that this is a subset of x cross y because it it can be defined as the collection of all members such that x, it's equal to x plus y. So essentially the range. And yeah, note that it's containing the entire range, right? So now we just have to show it's a continuous function. And that's pretty easy. So should I rewrite it that way? Yeah, it's fine. Yeah. So it's so what's an open set in the subspace topology of x, this set with respect to x plus y? So U cross V is going to be an open set in X cross Y. So the subspace is going to be, well, U cross Y naught, right? Okay. Or at the very least, it's a basis element. Since this is the basis, so the basis intersection can give you the basis of the subspace topology. I think it's not a theorem of the book, but I think I proved it. Yeah. So now if we show that this inverse image gives you an open set, we're done. Let's see. Yeah. Yeah. Now, yeah. So X gives you X plus Y naught. So U has to give you U. You just figure this one out. It's not that hard. Yeah. So are we done here? So it's U because, well, yeah, it's all contained in one point. Okay. Oh wait, you have to show it's a homeomorphism, right? Yeah, we're not done yet. We have to show it's an open map. Is it an open map? Yeah, an open map. Actually. So if U is open, f of U is equal to U cross Y naught. Now why is that? That is because U is an open set, and yeah, if you take any X here, you're going to get X cross Y naught. So yeah, you just take the union and you will get it. So, yeah, union doesn't transfer over. That's a bad idea, but yeah, it works out, I think. Like just it's because it's the identity function, I'm getting extra confused because the simpler it gets, harder I think, and I tend to overthink here. But yeah, the point is they're homeomorphisms. Oh wait, we're supposed to define the inverse map. Yeah, how do we define the inverse map? Yeah, so inverse f inverse of x cross y naught is equal to x. Yeah. So yeah. Okay, so if I just show it bijective just to be safe. So yeah, any x cross y naught you can get such an x from it. So yeah, we're fine. Now what? Now yeah. So because of that, because it's on basically the identity function f inverse of u cross y naught is u. F inverse of f inverse. So and that's precisely basically f of essentially this is the same thing as the image set of u cross y naught. Are we done here? Sorry, image set of u. Sorry. Uh, yeah, it's fine, I think. But yeah, it's a bijection. That's easy to show. It's inverse image. So this is an open set. Yeah. So this is a distraction now. Yeah. Inverse images of an open set is an open set because yeah, you can check that. And inverse images of an this open. Yeah. Yeah. Inverse images of an open set in the from the inverse function. Inverse function from x to x cross y. Yeah. The inverse function is we have an inverse function because it's a bijection, and again, yeah, if they're not equal in this coordinate, they're not equal in the set at all. So yeah, we get that. I have probably spent a bit too much time on this problem, but yeah, and the exact same method for G. I'm not doing that one. Okay, so yeah, question 5 is actually supposed to be quite trivial, but whatever, I'll do it. So let's see, what is the map that we have? F from A comma B. So we're taking the subspace topology to 0 comma 1. So f of A is equal to 0. It's a linear map. F of 1 is equal to B is equal to 1. So, or you know what, I'm going to define the inverse map. The inverse map can be figured out, whatever. Either way, I'm not really going to spend too much time on this. So, yeah, I'm going to assume that all linear maps are continuous. Okay, because of it is true because of the epsilon delta definition, and you can try it out. But yeah, just assume it to be true. It's not that hard to prove. Okay, so f of 0 is A, and f of 1 is B. Yeah, so that's A plus x into B minus A. right? Yeah. Okay, so this map is a homeomorphism from 0, comma 1 to a, comma b because let's see, yeah, it's a linear map. So I'm not, and the inverse map is also a linear map, and I'm not doing that. Okay. Now, actually, wait. Yeah, this is an order-preserving bijection, right? So yeah, that's you can directly apply that theorem. And so yeah, it's a whatever topology you take, order or subspace, it's the same, right? So the standard topology is defined from the order topology, but this is the subspace and the order topology, and this is an order preserving map, and therefore it's a homeomorphism. I think I did show that. And same thing with this one. The point is that you can just map 0 to the least member, and which is a, and b to the largest member, which is 1. So you can map those separately, and then you have the same problem. So yeah. Okay. Find a function that is continuous at precisely one point. Yeah, I did have one. So yeah. F from R to R. F of x is equal to x if x belongs to rational numbers and 0 otherwise. Is that it? Yeah. And you'll see it violates the epsilon delta definition at all points except 0. So the point is it's mirrored. Yeah. So at any point you take, you can always find a neighborhood that it's violating. Right. So it's one here, and that's a problem. So it's not satisfying it for all neighborhoods, and that's the problem. Yeah. Hmm. Okay. Suppose that it's continuous from the right. Show that f is continuous when considered as a function from RL to R. Hmm. Okay. That should be pretty simple. Yeah, RL to R, right? Yeah. Okay. So we just have to check for the basis elements, right? So the basis elements are mm, oh right, we have to first define what continuous from the right means in the topological context, or at least I'll try. Let's see. So A plus, yeah. So anything, yeah. Okay. Hang on. Yeah. So I thought about it. Let's see. So first we have to define the epsilon delta definition for this particular case. So for all epsilon greater than 0, there exists a delta greater than 0 such that, what is it? X minus x naught is greater than delta. So I'm not using the modulus here in this case. Right? Is that it? Yep, that seems to get. So x is, yeah, bigger than by delta. Yeah. Oh, sorry, that's it. Yeah. But delta is yeah. Okay. Hmm. Yeah. Implies f of x minus f of x naught is less than epsilon. Yeah. So now what? Now, yeah. So if so yeah, we just need the open set. We just need to use this to imply the open set definition and then we're done, right? and by that I mean number 4. So the open set f of q is contained in V1. So V is an open set in the standard topology, right? Now it will have a basis, right? And in that basis we have, yeah. So this is an open set in the lower limit topology, right? And it contains x naught, right? So yeah, we have a basis that's contained such that its image set is contained in the basis. So it's actually equal to the basis that's contained in V. And yeah, it's clear that yeah. So if we have any open set V, we have a basis that's contained in it, right? An epsilon basis, and we inside that we have an epsilon basis, right? And this epsilon basis is equal to f of u, and u is an open set in the lower limit topology. It's a delta set, but it's an open set in the lower limit topology, and yeah, f of u is contained in B, and this exists for all neighborhoods of x naught. Yeah, f of x naught, right? X naught is the point we. My bad. Yeah. So we have done that for any arbitrary point. Yeah. So it's given that this is satisfied for each A and R, X and X naught system. Okay, I can just tell you that the identity function is not continuous from RL to R to RL, right? Because this is an open set in RL, but this is not an open set in R. So yeah, and as maps from RL to RL, I have no idea. Yeah, I have no idea. So we are going to discuss this in chapter 3. So yeah, so be it. We'll discuss it in chapter 3, where I don't have to conjecture and I get the proof in front of me. Or the exercise gives me a hint, or I cheat. I don't know. I hope I don't cheat. Okay, let's have fun with question 8. It's a major question, and I did not screw it up. Screw it up. Yeah. So first of all, the order topology is Hausdorff. I proved it in the previous question, exercise. I'm not proving it again. So we do need that here. Okay. So if I show that the complement is open, I'm essentially using, yeah, if I show the complement is open, then we're done. That's one thing. And I'm also going to use this. So x does not belongs to a limit, imply if and only if there exists u of x such that u intersection a is equal to 5, right? That's probably it. Yeah, u is a neighborhood of x. So note that a closure is a closed set. So if a is not x is not belonging to a, if and only if this, right? So I'm using that. So if I manage to show that if x does not belong to a implies this, right? Then we get that a complement, because that's what we're assuming. We're assuming all subsets of x. A complement is open, right? Since a closure is closed. So its complement is open that way. So yeah, this is the argument in which will be proceed. So what does it mean for the set's complement to exist? So x such that f of x is greater than g of x, right? Is that it? Yeah. This set, if we manage to show that this set is open, then we're done, right? So yeah, that's all we have to do. Okay, so this is the same thing as saying, okay, this is not the same thing as saying, but this implies that f of x is not equal to g of x, right? Okay, now, yeah. So by Hausdorff condition, there exists an open neighborhood u of f and u of g such that f of x is in u of f and g of x is in u of f, u of g, right? And they are disjoint. So we've proven that it's Hausdorff, yeah. Now what? Yeah. So are we taking g or f? Yeah. Okay, this is a set in X. So f is f comma g from X to Y. Yeah, this is a set in X, and this is an open. this is these two are open sets in Y, right? Yeah. And okay, now their inverse images by continuity, since they're both continuous, is are yeah, they're both open, right? They're both open sets. And what else? Yeah, this open set contains, so we're taking an arbitrary x naught such that f of x is great. F of x naught is greater than g of x naught, right? And we're working with that. So we're working with this x naught essentially, right? Okay. Now this x naught, sorry, yeah, and this whatever. This x naught is what? It's contained in an open set, so we have a neighborhood of it, and yeah, so this x naught is going to lie here, right? These are neighborhoods of x naught, and these neighborhoods are such that they're contained in UF and UG. In fact, so f of UG, UF and UG are going to be contained in UF and UG. You get the idea, right? But these two don't intersect. And because these two don't intersect, and the intersection does transfer completely inside for this and this, these two also don't intersect the inverse images, right? So what does that mean? That means, oh, that's irrelevant actually, isn't it? Yeah, it seems to be then. Yeah. Their union, in any case, so we'll call this VF and VG. If you take the union, VF union VG, we got a neighborhood of X, such that, what? In fact, you can take intersection or union, doesn't matter, I think. We've gotten a neighborhood of X naught, such that it's by continuity, it's going to be contained in an open set. Yeah, I think we need intersection so that we can use both the continuity rules simultaneously. So this is contained in UF and UG. F of G is contained in UF and G of this thing is contained in UG, right? So this is an open set of X that doesn't that is not intersecting A at all. So yeah, we've gotten that. And from that we get, well, X naught is not in A closure from the theorem 17.5. Yes. So what does that imply? That implies that this is an open set. And yeah, that's how we show it. It's a bit of a long proof. Study every argument. And yeah, it's not that complicated, but yeah, you have to use the. Okay, I'll try to explain it better. If X is not in A, X has to be in this set, right? And by Hausdorff condition, there exists neighborhoods such that they don't intersect, right? You take their inverse images, they're going to be open sets. You take the open sets intersections, and right, that's going to be an open set. It's going to be a neighborhood of X naught, right? And it will not intersect A at all, because if it were to intersect it, then it will violate the Hausdorff condition, right? Yeah. Okay. Then, oh yeah, also note that these two neighborhoods are also, yeah, one small thing I forgot to mention. These two neighborhoods are such that since f of x is greater than g of x, every member of this neighborhood is greater than every member of this neighborhood. So that's an extra step. That would require some extra work. Yeah, I'm leaving that part out. How do we show it? I'll just think about it. Yeah, so they don't intersect. That's greater. Yeah, essentially, if this thing crosses over, and since it's an open interval, right? Oh, Yeah, we have to make sure it's a basis element. So take the basis element. You can always take the basis element, but don't take an open set. Take the basis element. So there is some work that has to be done here. Sorry. Yeah. So take the basis element that's disjoint. So because it's an open interval, it's going to be convex, and then you can use convexity to further your argument. So how do we do that? Yeah, that was essential. Sorry about that. Okay. Hmm. Yeah, so towards the contradiction, there exists an x naught such that it's lesser than it. Then essentially by convexity, they're going to, yeah, so let's say there's an x naught such that it's here, then there exists something greater than it, and they're going to because it's convex. So they're not just non-empty, right? The things between them exist, and they lie in both of them. So they have a common intersection. They have a non-empty intersection, and that will contradict our assumption, initial assumption. So that's how you do it. Once you've done that, then you can clearly show that it doesn't intersect it. But yeah, you have to take that basis. So there was a little bit extra work. Okay. Yeah. So now that we have two open sets, so f of x is less than equal to g of x is a closed set. G of x is less than equal to f of x is also another closed set. Their intersection is a closed set, and intersection essentially means we AND the properties, and ANDing these properties by total order, by totality, gives us f of x is equal to g of x, right? This is the intersection of both these sets. Yeah. So you have to AND the properties. And yeah, this is a closed set, right? Okay. So their intersection is literally such that f of x is equal to g of x. So we're almost done with the hypothesis of the pacing lemma. Yeah. So yeah, if h of x is equal to f of x when x belongs to A and g of x when x belongs to B, and since when it belongs to the intersection is equal, by pacing lemma, it is there exists a continuous function. There exists a continuous function such that is defined this way by pacing lemma, and that is identical to the one given in the question. So yeah. Okay. So yeah, I proved it's true for finite and heuristically in the theory portions. I'm not doing it again. It's not that hard. Essentially, use the principle of induction if you really want to get into it. You can you can use the pacing lemma in your induction hypothesis essentially, and note that to prove any theorem about finite sets, you need the induction method, the regular induction method. So yeah, that's how it's done. Now, if it's so I was thinking of a lot of complicated examples for B part, like the one that's not precisely continuous at precisely one point. So the example I thought of after the simplest example I thought of is essentially this. Yeah, f can be 0 at one point, right? And so we're defining f from what to what? Let's see. Yeah, z plus 2 r, right? So you have the discrete topology and it's open, or is it the other way around? Yeah, it's the other way around. No, it's fine. It's fine. Yeah. Okay. So wait, is it discrete topology? That's not helpful. Hang on. Yeah, I just think it's almost ready, but yeah. Yeah. Okay. So I had thought of the example. It was a decent one, but I had to modify it to suit the question, which I didn't really read properly. So let r equal to let's see, minus infinity comma 0 closed union 1 comma infinity, right? And then union n is equal to 1 to infinity. Yeah, 1 by n plus 1 till 1 by n. So is that the entirety of R? Yeah, yeah. And yeah, at 1, it's going to be equal to that, and at 0, it's, yeah, defined. So yeah, that's the entirety of R. So that's a countable set. Okay. Now, at these points, I'm going to define them as n, right? So for each, I'm going to call this an, right? Okay. So for each an, we have a function that is a constant function from f an to r. Yeah. And that's going to be defined as f is equal to n, right? So it's a constant function, so it's continuous. We don't have to think much, right? Here, it's going to be 0. So I'm going to call this C and D. I don't know why I skipped B. C, we have 0, and D, we have 1. Doesn't matter. Yeah, we're starting at 1. So what does it look like? We have 1, then we have 2, then we have 3, 4, 5, 6, 7, 7, 8. Goes on, then it goes to here. And yeah, as you can see, this is not continuous in any way. Oh wait, they're not agreeing on. Okay, sorry. How do we just turn it into a line essentially? How do we do that? Just, so it's starting from 1, so it's agreeing there actually. So 1, then at half till that we have to get 2, right? So n plus x, uh, just add a linear transformation. It's not that hard. But yeah, essentially it goes to here, and then at this point it's infinity. And we can do that because we can do that. So there's nothing stopping us. Yeah, so these are actually never going to contain, 0 is actually never going to be contained here, right? This union is going to be open 0, comma 1. So yeah, it works out. And this brings us to part 3, if it's locally finite. Yeah. So essentially, we just use spacing lemma on the locally finite part. So for all for all points in x, we have a neighborhood that intersects a alpha for only finitely many values of. Yeah. So there exists v such that v intersection a alpha is not equal to 0, phi for only finitely many alphas, right? So we can get a continuous function for each point essentially, right? Yeah. And then we can have a local formulation of continuity, and I'll have to think harder about it. So yeah. Yeah, so I solved all the problems and did all the ways, but yeah, so I didn't actually pre-solve them this time. So I did now, and let's record. All right, so yes, yes. Okay, so we're going to use the point-wise continuity because we need to use local finiteness, and that requires that's only given to us for every single point arbitrarily. So for any arbitrary point, we can use local finiteness. So that's why we have to use the point-wise continuity criteria, which is that one, number 4. Okay, so let x belong to x, and v is the neighborhood of f of x, right? Okay, now, yeah, x is in x, so x has a neighborhood b prime such that b prime is a complete subset of a1 union an. I'm just going to call these that, right? Okay, now f from x to y is continuous in this f restricted to a1 union. Yeah, union till an is continuous from part A, I think. Yeah, part A. Now what? Now, yeah, so it's continuous. So we're almost there. We just need to use that continuity. So we have a neighborhood of f of x, right? Yeah. So we need an open set in this set. So we just intersect it and then we're done, right? Right? Okay. Okay. So we have a neighborhood of, yeah. So V prime is a neighborhood of X. Uh, what? Yeah, this V prime is for the local finiteness, right? Now this would be a neighborhood of X, right? So why is it a neighborhood of X? Because f of X is in the V. Hang on, something's wrong here. Yeah, it's not V here. It's something else. It's probably S inverse V or something. Let's see. No, we just intersected V prime, right? Okay, yeah. So this V is the problem here. Okay. So what is actually a subset here? Mm, no, V is intersected. Hang on. Okay. Let's just start over. Okay. V prime is a neighborhood of X, right? Such that it's a subset of finitely many, right? Okay. Now what? Now we're going to use this soon enough. Okay. We'll just so first we have to use the continuity of X here in the set. So V prime is a neighborhood, right? In this set. So for that we have a neighborhood U of X such that f of u is contained in V prime, right? Okay. Yeah, we're close now. Yeah. Okay. So V is a neighborhood of X. V prime is contained here, and it's an open set. Yeah. Okay, but we need an arbitrary neighbor, right? And oh, right. Okay. Yeah. Either I did an incorrect position and I thought I was done. Yeah. But I think again, and then I screwed up something. But yeah, I'm just going to write it down and then explain that. So hang on. Yeah, so I wrote it and I think it works. So yeah. So let X be an arbitrary point. Let B be an arbitrary neighborhood of f of X. Now what? Yeah. So we're calling V prime the neighborhood that is the witness to the local finiteness of X of the entire space. So because X is locally finite, there exists a V prime such that V prime is completely contained in A1 to AN. So we're assuming the cardinality of the finite set, right? So I'm calling it this. And V prime is completely contained in it, and V prime is open in X, mind you, not the subspace topology, right? So it's not open in this topology, it's open in X, right? Uh, that's a little bit vague from the language, but I'm pretty sure that's what the local finiteness definition means. Okay, now I'm invoking continuity of F in this because by part A, so V is a neighborhood of Y. We don't care how it is, right? It can exceed f of A, whatever, it doesn't matter. Now, because of that, we have a neighborhood of X, U, such that f of U is contained in V, right? So that's invoking the continuity in here, right? And this neighborhood, however, is open in the subspace topology. So there is that, right? So we need to make sure that, this U, from this, we can get a neighborhood that's open in the bigger topology as well. So to manage that, we're expanding. That's where the intersection comes in, and I'm going to come to that. So U is essentially open in the subspace topology. That's exactly what's written here. W intersection in inter. Oh, it's union, doesn't it? Yeah, yeah. I got it. Here too. Yeah. So here, U is completely contained in AI, so it works out. It's not, it's not anomalous essentially because if we take something outside of AI, then we're going to get a problem. And V prime is completely, sorry, yeah, V prime is contained in AI, and yeah, we didn't need that, did we? Yeah. and U is an open set that's contained in V. Yeah, so that should be U, I guess. So what does that mean? That means this f of U is since this is an open set, right? This is an open set given to us. U is an open set given to us by continuity, so this is an open set. And f of U intersection V prime is contained in V, since f of U is contained, right? And this is an open set in the subspace topology as well. So it's open in X as well as the subspace topology. So what did we get now? For any arbitrary neighborhood of f of x for any x, we have gotten an open set U such that it's contained. And yeah, we had to use the hardware of the finite local sets. But yeah. So yeah, I just had to think a little hard about it. This is exactly the solution I thought of, but I just thought I was thinking that this V will cause a problem in Y, but we can just use the continuity directly. There's no problem. Yeah, let's get to question 10. Okay. I'm smacking it harder than usual. Anyways, yeah, so to solve question 10, we just need to apply the multiplicative, the map into product theorem. And for that, let's see, how do we use that? Yeah, we have a map F, how do you write it down? Yeah, so F cross G. Mm, so we're defining it that way, but okay, let's see. So how do I name the maps is the question. Let's see. Okay, I'm just going to call them pi of 1 of F cross G and pi 2 of F cross G. Yeah. And their maps from, let's see. Yeah, A cross C, A cross C to B to D, right? Yeah. So if both of these are continuous, then we're done, right? Yeah, we're pretty much done. Okay. So let's show that. Well, let's see. Hmm. Okay, so any open set U of P, right? Yeah. So pi in 1 inverse of B, sorry, U is equal to, well, let's see. So the other set will essentially be completely there, right? So C should be completely there. Yeah. So what should I call it? Oh yeah, it's going to stay as U. So U cross C, right? I think that's correct. Yeah, that should be correct because yeah, we're projecting from A cross C to essentially A, right? We're going from, oh, it's going to be D, I think. Yeah, it'll be D. Yeah. So we're going from A cross C to B cross D and then to B. Yeah. So it's going to be U cross D. Okay, so I'm just going to do it for pi 1. Pi 2 is similar. Now, yeah, so now we want F cross G whole inverse U cross B, right? Okay, what is this going to be? So this is an open set and this is an open set, right? So what are we given by continuous? Yeah, so F and G are continuous, right? Okay. Hmm. Okay, so if D is in the other side, on the other side, yeah. So D contains the range of contains the range of G essentially. So C has to be there, right? Why? Any member, yeah. So you just fix one point and then you vary across all C, so you're going to get the entirety of C. So that's why the inverse image is going to contain it. And by continuity, this is going to be an open function, right? So it's can we truly split it? Yeah, so we can, and I can't seem to be able to prove why. So take any u in here, u cross any member of D, we're going to get that. Yeah, yeah, it should be fine, I think. Yeah. So the sets themselves are as follows, right? And this is clearly an open set because this is an open set and this is an open set, and by definition, the product is an open set. So yeah, I think we're fine. So by that criteria, this is an open function. Sorry, continuous function. Yeah. Okay. So we have a definition for continuous in each variable. So let's check that out. Then we'll have an extra question to explore. Okay. So there's a one-way implication here, right? So f is a function from x cross y to z, not the other way we've done studied earlier. Yeah. hmm hmm Yeah. Okay. So we have h, that's a map from x to z, defined as h of x is equal to f of, I'm just going to call it h of y naught. Doesn't really matter what the y naught is here. Yeah. Okay. So h of x is equal to f of x plus y naught. And yeah, we have to show that this is a continuous function, right? Hang on, is this even? Yeah, it is a point in there. So yeah, we're fine. Okay. Okay. So you have to show for any arbitrary y naught in y. This is a continuous function. All right. So how do we do that? Let's see. Hmm. So I think we have to use the other theorem here. No, we don't. I hope we don't. So what would an open set in Z look like? Hmm. Okay, just some open set. Let's just take it U of Z. Okay. Now F is continuous, right? So hmm, so its inverse image, F inverse of U, is going to equal hmm, do you want to use the other criteria here? Okay, so I haven't actually attempted the question properly, but let's see what we can do. So I'm not going to expand too much on this, but there is a very clear homeomorphism. I'm going to call it G from x to x cross y naught, and it's the trivial map. G of x is equal to what? X cross y naught. So it's a homeomorphism. We have discussed this earlier. Okay. Now, yeah. So h of x is equal to f of g of x essentially, right? So this is a continuous function. Oh wait, are we done? So this is very clearly a continuous function, and this is a continuous function. Oh, this was easier than I thought. I think yeah, we're done. We're done. So you just need that this is a homomorphism. We're done. So yeah, that's it. Okay, it was easier than I thought. And same thing backwards. So yeah, this g of x is always going to be a continuous function, no matter what y naught we take. It's a singleton, and yeah, you're going to get one for each y naught. Yeah, I hope there is no doubt. Yeah, should be fine. Yeah, so you can just directly use the fact that the composition of two continuous functions is continuous. Yes. Okay. Let's solve question 12 now. Question 12, show that f is continuous in each variable separately. So let y naught be constant. So x y naught by x square plus y naught square, right? Yeah. If x, so let y naught not be 0 first, and then let y naught be 0. So if y naught is not 0, well, if y naught is not 0, then this thing is never going to be 0, right? So we're fine. It's a well-defined rational function. Is it rational? Yeah, it's rational. So yeah, it's because it's rational, it's continuous. I'm not going too much into it. If you want to really get into it, check using epsilon delta. How would you do it? Yeah, you can do it. It's not that hard. Like just how would you do it? Let's see. Hmm. Yeah, I think you have to use the fact that x and 1 by x is like kind of continuous. Yeah, so I think if you split it up a bit, since these are just constants, you get some sort of polynomial eventually. And yeah, it turns out to be continuous. Yeah. So it comes to the continuity of x to the power n for all n. Yeah. Okay. And if y is 0, well, it's just equal to 0. So we're fine. And it's continuous around 0 because, yeah. Actually, yeah, we don't care about that. We don't care about how it's changing across y naught, right? And yeah, the same argument holds if you flip the variable since the function is symmetric. Okay, so it's continuous in each variable separate. So yes, we do take the y naught as a constant. Now compute the function. Yeah, so that's pretty simple. G of x is equal to half if x is not equal to 0 and 0 if otherwise. And if you take the open interval, what do we take it? Yeah, minus 1 to 1, right? Yeah, so the inverse image is essentially going to be what? Okay, yeah, let's not take that. Let's take it as, or is it fine? That should be fine. Hmm. Yeah, just take 1 by third to be safe. Yeah. So this is an open set and it only contains the point 0 and the inverse image is going to be 0 and a closed set. So it's not continuous. Show that f is not continuous. Well, let's see. So yeah. Okay, so is g of x continuous? Yes, it is. So observe that there is a homeomorphism from x to x such that I'm going to call it h of x is equal to x cross x. Now, why is this an open set? Yeah, so any open set here is going to be of the form u cross v, and its inverse image is going to be oh, maybe it's not a continuous function. Let's see, maybe it's not. Yeah, so any open set is going to be of the form u cross v, right? Hmm. Yeah, it won't have a yeah. So if they're different, it's not going to have one you know that thing. Yep, perhaps it isn't. Okay. Hmm. Okay, is the other, yeah, the pi projection thing is definitely a continuous function, I guess. So that should be fine. Okay, so show that f is not continuous. So how do we have to use composition, that's clear. But how do we use that? So g is not continuous and g should be the composition of two functions, right? So g is a function from x to, yeah, sorry, r to r, right? So it's a function that's going from r to r cross r to r, right? So it's yeah, yeah. We really need to show that this is a continuous function, otherwise it is kind of screwed. Okay, so yeah, so I thought about it and I was close. This is not actually the product topology of X cross X. This is actually the subspace topology of all the subspace subsets of R cross R such that X and Y are equal. So it's a subspace topology, not a product topology. And yeah, so then we're using the injunction thing. What is it called? Inclusion, yeah. So the inclusion function is continuous, right? From that subset to R, and that composed with the big function f is going to give us a function. It's going to give us a function from the subspace of R cross R such that x and y are equal, and on that we can get a continuous function from R to x. That subspace. Yeah. So that would be a continuous function. So yeah, I'm not writing them all down, but yeah, everything I said is correct, I think. So we have a subspace and we have an inclusion function from that to R, right? And from R to that subspace, there's a continuous function because it's the set of all points where the coordinates are equal. So yeah, we're fine. Okay, now the question I actually solved. I think we'll be able to do this one at least. So without any hiccups. Okay, so you have f from A to Y, right? Yeah, Y. And we're saying if there's an extension from A till A closure, right, then it's unique. So if there exists a G prime from A to A closure, sorry, A closure to Y, then they're both equal, right? So let's proceed towards the contradiction. Let them not be equal for some X in the limit points, mind you. So let X belong to A prime and G of X is not equal to G of G prime of X. So it is important that it's a limit point and you see it in the proof, but so that's also one of the conditions for extending from F to G. Yeah. Now, since Y is Hausdorff, we have U X, U prime and U such that they're both containing, the respective ones. So U prime is containing G prime and U is containing G and they're adjoint. Yeah. Now, since G is a continuous function, just check. Yeah. G and G prime are both continuous function. Their inverse images are going to be open sets. So let's continue with that. G prime inverse and G inverse. They are open sets, right? Yeah. Now, because they are both open sets, their intersection is also an open set. And because they're both essentially containing the outputs of X, they're both going to contain at the point X. And since they're both a neighborhood around X by definition, and X is a limit point, they're going to intersect A in a point other than X. So let's call that point Y. So essentially, I'm going to call this V. V intersection A is minus X. Y belongs here, right? So it's non-empty, so let Y belong here, right? Yeah, now comes the problem. So Y is actually in A, right? So that means f of Y is equal to G of Y is equal to G prime of Y by definition, right? So what now? Now that means, yeah. Now that means, Y, or at least this point of from Y is going to lie in all these neighborhoods because that's how inverse images work. So if Y is in V as well, then it's going to lie in this neighborhood as well as this neighborhood. Sorry, U prime and U. But that contradicts the assumption that they were disjoint. And because of this contradiction, it must be unique. So yeah, we're done. Yeah, bye.